Welcome to our webinar entitled Enabling Experimentation in Classical Control with MATLAB Simulink Real-Time Windows Target. My name is Eniko Enikov. I'm an associate professor in the Aerospace and Mechanical Engineering Department at the University of Arizona. With me is my student Joshua Gill, who was instrumental in the development of many of the features of this project and will assist me in the demonstration of the experiment. The topics of this webinar include motivation for the development of the experiment, description of the hardware, development of a dynamic model, development of a real-time Windows target application which is used to control the experiment, identification of the parameters of the system, design of a closed-loop controller based on the principles of classical control, and assessment of the project using student feedback from the first offering of the class. The primary motivation behind this project is to provide our students with hands-on experience. Some of the benefits of hands-on laboratories include learner-centered education, ability to engage in problem-based learning, which connects theory to practical experience. However, oftentimes, offering laboratory sessions requires dedicated room and space. It could be costly due to the price of experimental equipment and the need to pay a teaching assistant. Therefore, our design objective was to develop a portable and inexpensive experimental apparatus that students can acquire for the fraction of the cost of a textbook. Our students work in small groups without the need of supervision, or they can also work at home using individual experimental stations. The hardware setup consists of a light carbon rod attached to a plastic stand via a low-friction potentiometer. The opposite end of the rod has a small DC motor driving a 2-inch propeller. The output voltage of the potentiometer is discretized using a 12-bit analog to digital converter and is sent to MATLAB via USB protocol. MATLAB automatically adjusts the offset in the signal by subtracting the initial value and multiplies it with the predetermined gain to convert the voltage into an angular reading. The desired control signal is then fed back to the motor using a pulse width modulation. An H-bridge circuit is used to allow bidirectional operation, that is, positive control signal drives the propeller in the forward direction, negative control signal drives it in the reverse direction. Let me now turn to my student Joshua, who will give you a tour of the actual system.
This is the Aero Pendulum, designed and built at the University of Arizona Advanced Microsystems Laboratory. The remainder of this presentation will be about the design, analysis, and implementation of this mechatronic system. The Aero Pendulum rotates on a small, low-friction potentiometer that allows the microcontroller to encode the angle of the pendulum at any given time. The Aero Pendulum's rod is made of carbon fiber and contains a small DC micromotor at the free end. This DC micromotor is capable of spinning the attached propeller in excess of 8,000 radians per second. The low-cost, custom-designed data acquisition board contains a PIC microcontroller which performs 10-bit analog-to-digital conversions, as well as supplies the H-bridge with appropriate pulse-width modulated signals. This data acquisition board is supplied 9 volts and communicates with the host computer through a USB to RS-232 conversion cable.
The first assignment which we give to our students is to develop a mathematical model of the system. Students typically do so by writing the conservation of angular momentum. J times theta double dot is equal to the moment provided by the thrust force of the propeller T times L minus mgl sine theta, which represents the moment of the gravitational force, and minus C times theta dot, representing a small frictional torque. Next step in the modeling is to obtain a relationship between the thrust force of the propeller and the input voltage U. This is represented here by a linear law T equals to K times U, which is only an approximation. In real life, the thrust force of a propeller is a function of the rate of rotation of the propeller, omega, and the relative velocity of the air, which in this case is theta dot. We do not use this more complicated model, but those of you interested in it could get additional information from a master thesis of one of my students. The next step is to examine the model at steady state, that is the condition where theta dot and theta double dot are equal to 0. Under steady state condition, the model relates the steady state angle to the steady state input voltage USS, and students are able to plot this relationship as a linear proportionality law relating the steady state USS to sine of the steady state angle theta SS. This allows them to determine the constant K over mg, which is later on used in the development of a full model of the system. Before asking the students to develop a real-time Windows target interface, we teach them how to use Simulink. For this purpose, we provide them with sample values of the parameters of the system, and we ask them to build a block diagram representation of the equation of motion. You could see an example of this block diagram here. Students can use various step inputs to produce simulations of the response of the system. Then they can compare these simulations with experimental data and fine-tune the parameters of the model. Good familiarity with Simulink is quite essential, as Simulink is the general interface used for real-time Windows application as well. We're now ready to move to the next topic of this presentation, that is using the Simulink Real-Time Windows Target Interface to operate the hardware. Simulink Real-Time Windows Target, or RTW, is an interface that allows hardware to be integrated into the control loop and run in real time. We find it easy for students to use because they can modify their controller designs and simply replace the transfer function embedded into the RTW, then compile the model and run the pendulum in real time. We utilize packet in and packet out blocks to communicate with the microcontroller operating the pendulum, and in doing so we've been able to reduce the sampling time down to 5 milliseconds. This faster sampling rate allows us to do more advanced studies, for example collection of frequency response from the pendulum, which was not possible in the previous version of this experiment. Let me now turn to my student Joshua, who will guide you step by step in configuring each of these blocks and obtaining an open loop response.
Before I show the development of the real-time Windows target interface, I will first discuss how our system communicates with the host computer. Our system communicates through a USB to RS-232 conversion cable. The peripherals driver creates a virtual COM port on the host PC, which allows MATLAB and Simulink to easily read and write for high-level access to the mechatronic system. To command the microchip microcontroller to deliver a specific pulse-width modulated duty cycle to the motor, the host PC must send the microcontroller an 8-bit value with 7 bits representing the duty cycle and 1 bit representing the sign of the signal. The motor is driven by an H-bridge, shown on the printed circuit board, which allows current to flow both in the positive and negative direction through the motor, allowing for forward and reverse motion of the pendulum. When the microcontroller receives the signal, it will correctly apply the duty cycle as dictated by the PC. When the host would like to retrieve the angle of the pendulum, it must send 255 to the microcontroller. When this value is received, the microcontroller performs an analog to digital conversion, reading the wiper voltage of the potentiometer. It then returns 2 bytes containing 10 bits of data representing the digitized voltage. This voltage is then multiplied by a potentiometer coefficient, which is the effective rotation of the potentiometer, divided by the maximum 10-bit value, 1024. The result of this multiplication directly represents the angle of the pendulum. Before we can run a model in Windows Real-Time Target, we need to complete the installation, as MATLAB does not do this automatically. To do it, simply type in the command window rtwin target setup and confirm. As soon as it finishes installing, you can now use Real-Time Windows Target. When you open up a new Simulink model, there's a few settings that need to be changed before Real-Time Windows Target will work properly. The first thing you need to do is go up to Simulation and then Configuration Parameters. When Simulink runs Real-Time Windows Target, everything is discrete, so we need to change the solver type to a fixed step solver. and we'll choose discrete no continuous states. The other thing we need to change is inside the real-time Windows target settings. We need to change the target file from the generic real-time target to the real-time Windows target. Select realtimewin.tlc, and now the configuration is complete. Now that our model has been properly configured for real-time Windows target operation, we need to go to the real-time Windows target block set. Inside this block set, there are several different types of inputs and outputs. The ones we will choose for our model are the packet input, packet output blocks. These blocks send unformatted binary data across the serial port, which is important because the data we are sending does not represent characters, it actually represents values. The first block we will add to our model is a packet output block. This will be responsible for sending the duty cycle to the microcontroller. We need another packet output block, and this one will be responsible for sending 255 to the microcontroller. When the microcontroller receives this value, it will recognize it as a signal to perform an analog to digital conversion. Once the analog to digital conversion has been completed, it sends back the 2 bytes of data. To capture this data, we will add a packet input block to the model. Now that our inputs and outputs have been added, we need to configure the output and input blocks. To do this, we can double-click on the packet output block and create a new acquisition board. When we click Install New Board, Simulink builds up a list of available boards it knows how to deal with. Our board is a custom design board, so we will use a generic serial port. Our board is currently hooked up to COM5. Its baud rate is 19.2K, 8 data bits, no parity, and 1 stop bit. We can choose a sampling time of 10 milliseconds, and when we send a duty cycle to the microcontroller, it's 7 bits of duty cycle and 1 bit of sign. This fits into 1 packet, and the packet sign size is an int8. If we open up the second packet output block, we see that the board has already been installed. We can open board setup just to make sure that all the settings are correct. And they are COM5 19.2, 8 data bits, no parity, 1 stop bit. And we'll choose the same sampling time of 10 milliseconds. When we send 255, that also fits into 1 packet. We'll send it as an int8. For the packet input block, we'll use the same data acquisition board as the packet output blocks, but we actually need to change the data type. Since we're receiving 10 bits of data, that doesn't fit into 1 packet. So we're actually going to need to have our data size be 2 packets and have an unsigned integer that is 16 bits wide. Since we have 2 packet output blocks in the same Simulink model, both talking to the same serial port, at every sampling time, the first packet output block will send its data, and immediately after the second packet output block will send its data. This is important because the duty cycle will always precede the angle reading. To run the simulation, you first need to build the model. To build the model, you can simply click the incremental build button. Once the simulation has finished building, you can see in the bottom corner it says ready. Now you can connect to the external target and click play. Play will then execute the model.
Now that we know how to operate the pendulum in open loop mode, we can use this to obtain some of its parameters. Recall from the previous slides that the steady state input voltage USS is related to the sine of the steady state angle theta SS through a proportionality law with the slope of K over mg. We therefore assign the first experimental homework to students to obtain this curve experimentally. Soon after they start experimenting with the model, they realize that for very small values of the input voltage USS, the pendulum doesn't move. In fact, even the motor doesn't turn. They need to reach a value of approximately 22 to 23 before they notice some deflection of the pendulum. A similar effect occurs for negative input values of USS. So this is the first time the students encounter a nonlinearity in the physical system represented by a deadband phenomena. They also find out that when they apply positive inputs, they obtain one value of the slope. When they apply negative inputs, they obtain a different value of the slope. This represents the difference in the efficiency of the propeller going forward and backward. To overcome the deadband phenomena, students first need to write the proper expression for the thrust force as a function of the input voltage U, represented by this equation. And then it is easy to see that by applying a control law, also a nonlinear control law that offsets the U by U0 in the positive direction and by minus U0 in the negative direction, we can collapse the dead zone into a single point in the origin. So by introducing a variable U bar equals to U plus U0 for positive input voltages and U minus U0 for negative control voltages, the new thrust of the pendulum is given by Kp times U bar for positive inputs and Kn times U bar for negative inputs. This remains a nonlinear law because the Kp and Kn parameters are not equal to each other. However, in the remaining part of this experiment, we will be driving the pendulum in positive direction only, so we will always stay in the upper branch of this law, and for our purposes, the pendulum will behave as a linear system. We now turn to the remaining nonlinear term in the equation of motion, represented by mgl sine theta. To eliminate this term, we apply yet another nonlinear feedback control law, represented by change of notation from U bar to U tilde. By adding mg sine theta over k, we cancel the nonlinear term in the equation, and in terms of U tilde, the system now becomes completely linear. This is the so-called method of feedback linearization, which we also used in the previous slide when we dealt with the elimination of the deadband. We are now ready to illustrate the effect of feedback linearization on the real system. Consider the case when U tilde is equal to 0. Under these conditions, the solution of the equation of motion are represented by a constant term theta infinity plus an exponential transient term that decays to 0. We therefore expect to see a pendulum that remains stationary at any particular angle. The block diagram representing the gravity elimination, that is the cancellation of the mg L sine theta term, is shown here. Now let me turn to my student Joshua again, who will show us a demonstration of this system.
To demonstrate that the linearizations were successful, I have created the Simulink model on the right-hand side of the screen. In Pendulum I/O, that's simply a grouped block of what I showed earlier in the presentation, of designing the input and output blocks with real-time wind as target. This section right here is the motor's dead zone compensation. We take the sine of the control signal we are about to apply to the motor, and we multiply it by the coefficient 23. 23 was determined by applying incrementally small duty cycles to the motor. At a duty cycle of 23%, the motor barely spins. This section right here is the feedback linearization of gravity. We take the sine of the angle the pendulum is currently at and multiply it by the coefficient s. After running a few experiments, it is determined that this pendulum's coefficient is 69. If I run this Simulink model, I should be able to put the pendulum in any position and it should stay where I put it.
We are now ready to design a closed-loop controller for the linearized system. Notice that the Openloop Transfer function has two parameters, k over ml and c over ml squared. Also notice that it the system is of type 1. Therefore, if you attempted to apply a unit step input to the Openloop transfer function, you would obtain an increasing or monotonically increasing output representing the integral term, that is the pole at the origin. A more practical way to identify the parameters of the system is to apply a unit feedback. Under this condition, the system will have a zero steady state error, and the parameters of the system can be obtained from the transient response. To extract the parameters of the open loop system, students first compute the closed loop transfer function g prime. It is easy to see that the square of the natural frequency omega n is equal to k over ml, and its product with the damping ratio zeta is equal to the parameter c over ml squared. With the developed real-time Windows target interface, students are now able to easily implement a unit feedback control of the pendulum. This plot shows the response of the pendulum to a step input of 40. It can be seen that the steady-state error of the system is negligible, as one would expect for a type 1 system. The natural frequency omega n can be determined from the 90% rise time, which comes out in this case to be 0.35 seconds. Omega therefore is approximately 5.07 radians per second. The damping ratio zeta can be determined from the percent overshoot, which in our case is about 50%, resulting in a damping ratio of 0.2. With the formulas from the previous slide, the two parameters of the open loop system can be easily computed. With the fully linearized and identified system, we are now able to give the final assignment for this project. We ask the students to design a dynamic compensator that reduces or eliminates the overshoot and maintains a maximum of 5% steady state error for command inputs up to 55. This value is limited by the power of the motor. We give them a hint to place the gain crossover frequency at 10 radians per second and increase the phase margin there by 60 degrees. I have asked my student Josh to complete this assignment using MATLAB's single input, single output SISU toolbox.
To design a phase lead compensator, we were going to use MATLAB's SISO tool GUI to help us. The first thing we need to do is define our system in the form of a transfer function. Now that we have our transfer function defined, let's go ahead and open SISO tool, and we'll point at that function. Okay, here's our uncompensated system. To design the lead, the first thing we will do is place a 0 right around 3. And we'll put in a pole right around 30. And the next thing I'll do is adjust the gain so the crossover frequency is at 10 radians per second. Now I'm going to go ahead and export our compensator to the workspace. We're going to name it C. And back in the workspace, that is our compensator. Now Simulink uses discrete mode to run all of its real-time Windows target simulations. So we need to convert this compensator to a discrete mode. To do that, we will use MATLAB's C to D function. And we'll use a zero order hold method for calculating the transfer function. And there's our compensator. The controller shown in the upper left-hand corner of the screen is the closed-loop version of the Openloop controller shown previously in the presentation. The Pendulum I/O block contains the packet input, packet output blocks to run the physical system. Inside lead controller, we have our feedback linearization, our motor dead zone compensation. We also have a linear transfer function block, which can be found in the control system toolbox. This block points to a variable in the workspace called CD. When we exported our compensator in CISO Design Tool, we exported it to the workspace and then converted it to a discrete function and saved it in the variable CD. The LTI block in the lead controller points to this variable. Once the compensator has been exported from CISO Design Tool and converted to a digital controller, the only thing the student needs to do is recompile the Simulink model as the form of the transfer function may have changed. Once it has been compiled, the model can then be ran, and the results can be analyzed.
To demonstrate the ability of RTW to implement higher order controllers easier and fast, we have developed an additional exercise where we require the students to increase the DC gain of the system by a factor of 5 without affecting the speed, that is the gain crossover frequency and phase margin. This can be accomplished by adding a phase lag term in series with the already designed phase lead compensator. I have asked my student Joshua again to complete this exercise using the SISU tool.
Now that we've successfully designed a lead compensator, we want to move on to the next exercise, designing a lead lag compensator. We're going to start with the lead compensator that we designed earlier. To make it a lead lag compensator, we're first going to add a pole around 10 to the minus 1. We're also going to add a 0 around 0.7. Now we can adjust the gain to make the crossover frequency at 10. We notice our phase margin hasn't really changed from the previous example, and our crossover frequency is approximately 10. We can also notice that our gain has changed to 8.6 from 1.24. This satisfies the requirement in the problem statement. To demonstrate that our controller works, I've exported the compensator into the workspace. I'll now connect a target in our Simulink model.
This concludes the technical portion of this presentation. I would like to share next some of the feedback we have collected from approximately 100 students who took this project during its first offering. Approximately 72 students selected the hardware-based project over a paper-based one, which was completed by 27 out of the 100 students. We conducted an anonymous survey, which was a volunteer-based survey, and 26 students participated in it. The following table summarizes some of the findings of the student survey. As you could see, the majority of the students appreciated the effectiveness of the pendulum experiment in demonstrating the relationship between the physical system and its transfer function, the response of a second-order system, the relationship between stability and the closed-loop gain, as well as the overshoot and the gain. In the first offering of this class, we used root locus as a design method, and therefore most of the students appreciated its application to the design of a closed-loop controller. They did not see the use of SISU tool and body plots, and corresponding response was low. The system type and its effect on the steady-state error was also well illustrated, and students were able to touch physically the system and introduce disturbances and observe the impact of the closed-loop control on the response of the system. We have further asked the students how long did it take them to complete the project, and the average number of hours was 8.8. We also inquired whether or not they needed a dedicated laboratory and how much time they require from a teaching assistant. Most of them felt that 1 hour per week was sufficient, and they did not need any dedicated space to complete the lab. In conclusion, I would like to recap the main topics that were covered in this presentation. We discussed the development of a dynamic model, the design of an open-loop real-time Windows target model, dealing with nonlinearities and eliminating them using feedback linearization, identifying the parameters of the system, designing a closed-loop controller using SISU design tool, conversion from continuous to discrete domains, and demonstration of a phase lead and lead lag compensation. Finally, the presentation reviewed some of the student feedback from this project. Lastly, I would like to acknowledge the support from a grant by the National Science Foundation and the contribution of my other graduate student, Mr. Vasko Pulizoev, who developed many of the hardware for this project. For further information and inquiries, please visit our website at www.nano.arizona.edu/mechatronics. Thank you.